My name is Jim Wallace, and for the next 30 minutes or so, I'm going to talk about designing security into low-cost IoT subsystems, or subsystems rather than subsystems. I've been working with ARM for the last 8 years. Currently, I'm working as part of the Systems and Software Group with a main focus around systems and aligning our messaging across the diverse product range that we have, from security IP to system IP to software enablement and to tools. So as I say, this morning I want to focus on security side of things and designing security into low-cost IoT subsystems. If we look at the IoT space, it is a vast and potentially huge market area, but it consists of many different markets. I think Eric yesterday talked about the potential of 1 trillion sensors over the next 10 years. And if you bring it even closer back in, by 2020, I've seen numbers of 50 billion units, which is huge. But if you start to kind of break down and segment the market a bit from, let's say, wearables, where you may have a handful of devices, and as these devices get integrated into clothing, that will increase. But then you go from wearables to smart health to smart home, where you may have 10s, 20 plus devices or smart devices in your home, to smart cars, and as they become autonomous, you could have 50 plus devices in those cars, or next generation of cars, to smart factories, to smart cities, where you potentially have million plus devices. And if you start multiplying those numbers up, you very quickly get into the billions of units. I think Gartner predicted that by 2020, there will be at least 1.8 billion units shipped in that year. But so in this, let's say, new IoT world, it will generate new opportunities, new ecosystems, and new business models. But for it to succeed, it will require open standards and also trust. And again, Matt talked a lot about that in the previous presentation. You will also need, let's say, key connectivity standard stacks, the ability to be able to manage these billions of devices in the marketplace. And also, I think Eric talked a little bit about let's say, the energy efficiency of these devices as well, particularly as we move from battery-operated to energy harvesting. If we do this all correctly, and we get the security and the trust right, then we can improve the productivity of the developer and make sure that they focus on the differentiating part rather than having to reinvent the wheel continually. As I said, this market is huge. And if I look at the connected home for a minute, and I focus in on the smart meter, IoT is going everywhere. The smart meter, we can see it's been deployed right across, say, the world, but it has a wide attack surface. So it links to the server, but it also links through, let's say, a base station to many products within your home. Criminals will hack this device. They can, if they're able to hack the device, they can potentially find out if you're home or not, which is not very good for you. Hackers could also attack and update records and stop supply or energy supply. Again, that could be very disruptive for you. So we need to think carefully about this attack surface. This attack surface is pretty wide. If the product becomes successful, and it will be successful, it will be attacked and eventually breached. And we need to make sure that we have things in place to be able to update and fix those breaches. What we'll also see is the IoT space has a whole range of different products, from ultra-low-cost products that potentially will use a Cortex-M0 class device to low-cost devices, which again will use a Cortex-M3 or M4 or M7 class product, either in a smoke detector or a smart meter type product, right up as far as generic products like security systems or smart home heating systems, will use either, let's say, Cortex-A class device. They will have different levels of security. So in the simplest form, the radio link, we will encrypt the radio link with AES encryption. As you move from low-cost to generic devices, it will start to integrate more hardware-backed security like cryptography or random number generation, but it will have the ability to be able to manage security, be able to update the firmware over the air throughout the lifetime of the product. So again, what you'll see is there will be a mix as you move from ultra-low cost to generic type products. What we're also seeing is a move to, let's say, generic devices. Again, taking the smart home and security system within the home. Today, you have a multitude of sensors around your home that connect to a central unit. What we're seeing is a move to that central unit where most of those sensors actually get integrated into that central unit. So again, the intelligence of that unit goes up. It could have a camera, microphone, a whole range of different sensors to be able to do, let's say, face detection, voice recognition, motion sensing. It could have the ability to be able to understand or recognize breaking glass, unusual sounds, and act accordingly. So again, what we're seeing is a lot of the, let's say, machine learning will start to move into these devices. They will, let's say, update their algorithms offline, but in effect, they'll be fairly autonomous products. So a lot of the raw data does not need to be sent to the cloud. Only processed metadata needs to be sent. In doing that, we can reduce the bandwidth, we reduce the, let's say, the cost, but also, more importantly, reduce the attack surface and increase security. So if I look at, let's say, in terms of these endpoints, what are the key things that we need to think about from a security point of view? And this is not exhaustive. There are many more things, but it gives us a feel. So from a device security point of view, we need to be able to protect from untrusted software, so attacks from untrusted software. We need to be, and if we do get attacked, we need to be able to recover from that attack. We need to be able to protect the firmware that's already on the device so that a competitor will not take or copy that firmware. We need to be able to keep data confidential. We need to prevent, also we need to be able to prevent that data being altered. And if someone basically has the wherewithal or the money to actually do a physical attack, we need to also have anti-tampering technology in that. Communication, we need to be able to encrypt the link. We also need to be able to authenticate the device on the network and making sure that we can identify the endpoint to the server. And then from a management point of view, right from the very beginning, we need to inject secure keys. We need to be able to securely boot that device. But throughout the lifetime of that device as well, we need to be able to keep the firmware up to date and make sure that we monitor behavior on that device. So I get three key areas, let's see: device security, communication security, and management security. As I said, security needs to be built in at all stages of the system. And particularly, say, when we are addressing these low-cost devices where designers may have little experience in integrating security into the system. So it needs to come pre-built in the software and also in the hardware. Now, if I start with the kind of low-cost or MCU class devices, what ARM has done is ARM has created a mbed device platform, and that includes a whole range of things from services to partner ecosystem to tools to technologies. And these include, and I'll touch on some of these as we go through the presentation, these include mbed device server, it includes mbed device connector, it includes the mbed TLS, mbed client, and mbed OS. If I start with mbed device connector, mbed device connector allows developers to connect IoT devices to enterprise software and cloud stacks through REST APIs without having to build the cloud-based infrastructure themselves. That's a major step, right? So instead of having to reinvent the wheel, they can focus their efforts on building web applications and differentiating their product. It also provides security and simplifies and gives the capacity to those developers to test out their ideas before they move to main production. So a lot of that is available. So the documentation, the software examples are all available at connector.mbed.com. So you can build your device, you can connect your device to the web, you can build your applications with example code, and you can utilize cloud-based solutions, whether it's IBM Bluemix or Microsoft Azure. On the client side, we have Mbed OS, and this is an open source embedded software system designed specifically for low-cost devices. It has been designed from the ground up to work with M-class type devices. So it's modular, it's secure, it's open source for the IoT space. It connects to the Mbed device connector, and it provides the following security in terms of communication security, management security, and device security. So communication security is provided through the Mbed TLS. Management security, again, we're able to, right from the very beginning, to inject the secure keys to security boots, and also through the lifetime of the device, be able to identify, configure, and update that device. And device security is implemented by the microvisor, again, which makes the most of what you have. Using the MPU, it can provide secure isolation on the device. Mbed client, Mbed client is a subset of Mbed OS. It also connects to Mbed device connector. It is OS agnostic, so it enables you to port to a range of different OSs from RTOS to Linux-based OSs. The security protocol is also similar to Mbed OS in terms of it uses TLS to provide a secure link. And then that Mbed TLS, what it is a library that enables cryptographic and SSL TLS capabilities in connected embedded products. So we support, in terms of SSL, version 3. For TLS, we support 1.0, 1.1, and 1.2. It's developer friendly in terms of we have clean APIs and documentation. The open source is available through tls.mbed.org, but it's also available as a standalone version for use in non-Mbed devices. So it's suitable for both Cortex-M and Cortex-A devices. It has a whole range of cryptographic blocks. So in terms of symmetric encryption, public key algorithms, hash algorithms, it has random number generation in terms of, and also is compliant with the X509 standard for PKI. And on the right-hand side, just showing you in terms of, as you go through the various years from 2011, I think up as far as 2015, these are, let's say, known vulnerabilities that we have found and fixed with Mbed TLS. So Mbed OS closely integrates with Mbed TLS and also the microvisor technology to provide device and communication security. If I look at the existing these existing low-cost devices, they use flat address space with little privilege separation. What Mbed microvisor is trying to do, it's a supervisory kernel that creates isolated secure domains on the, let's say, M cores, the M3, Cortex-M3, the Cortex-M4, and the Cortex-M7, by using the memory protection unit. So that basically gives us a normal world, or let's say an exposed world, and a secure world. So it splits the security domains into exposed code and protected critical code. TrustZone, our TrustZone for V8-M, we launched back in November of last year, and that improves the efficiency and security. So this is really hardware-backed security. With TrustZone for V8-M, we implement a hardware switch, so we can actually switch from the normal world to the secure world in one clock cycle. So the V8-M architecture introduces secure and non-secure code execution, so normal world and secure world. So the code running in the non-secure memory can only access non-secure devices in memory, while the code that's running in the secure memory can access the whole address space. So we now basically, on low-cost devices, non-trusted applications installed in non-secure memory can only access the normal world and cannot be used to attack the system. Behind that, we have hardware-backed CryptoCell technology, and that provides a range of security subsystems for accelerating and offloading the main core. And I'll talk about CryptoCell in a little bit more detail in a minute. So what we have now is a complete platform, security platform that can address the Cortex-M family, the low-cost devices, right up as far as the Cortex-A class devices, the generic devices. So for IoT, we have a complete story, security story, hardware-backed with roots of trust using the CryptoCell technology, the CryptoCell 310, addressing the microcontroller market space, and the CryptoCell 710, addressing the applications processor space. We've also, as everyone knows, we've been working very closely with the Linaro team and have integrated the trusted firmware with Opti. And this is all about reducing fragmentation, helping accelerate the latest ARMv8-A platforms. Trusted firmware is a reference design for implementing secure world firmware. It's broken into two key parts: trusted board boot and secure world runtime. The trusted board boot authenticates firmware and prevents malicious firmware from running on the platform by authenticating all the firmware images up to and including the normal world bootloader. While the secure world runtime enables world switch, interrupt routing, the power state control interface, SMC handling. And this is all available as open source as part of the GitHub, GitHub.com, and the address is just there. The latest version, version 1.2, includes trusted boot, baseline features, PSCI, version 1.0, and support for GigV3. So the underlying, so the combination of TrustZone, the trusted execution environment, and the CryptoCell technology are providing, let's say, platform-level security with hardware roots of trust anchor for the system, key management, and provisioning. And this really comes through, let's say, the CryptoCell acceleration, the modular approach that we have to CryptoCell, and of course the random number generator. As I've shown, these devices are modular and they can be targeted to different applications. So in terms of the MCU or low-cost devices, where area and cost becomes important, we have the 310 device. And in application of generic devices, where performance is important, we have the CryptoCell 710. We have a range of cryptographic, asymmetric and symmetric algorithms, standards-based, and we have a complete range of security resources. So again, implementing roots of trust, lifecycle strategies, key management, and provisioning. So coming back to the original, let's say, diagram that I showed you. So by using these technologies as the underlying platform, Light is enabling a secure foundation right across. And again, coming back to the secure meter, from the secure meter back to the server, and the secure meter into the home through the secure base station, and across, let's say, these secure devices within the home as well. So what we're trying to do here is provide hardware-backed security at the chip level, but also, together with Linaro and in the Light group, create a foundation of open source security software. We still have a long way to go, but together we believe that we can secure and make sure that we have a secure system. So imagine a world where you have a wide range of ARM-based devices. You can choose the perfect one for you, and that could be dependent on the price, performance, power, form, and security that you want. You pick the software you want to run on those devices, and that could be Android or Brillo. It could be, on the server side, Red Hat or Snappy. And once let's say you've made that choice, it should all just work together. And that, again, is what I believe the Light working group is going to focus on. So ARM and Linaro are going to work together to make this happen. So Linaro and ARM are providing this foundation for IoT. We're working together to provide this end-to-end open source IoT framework for specific IoT implementations. The Light working group is the place to collaborate on the ARM architecture, and this group will enable the next generation of open source software solutions that will map across the complete family, from low-cost Cortex-M devices right up as far as generic Cortex-A based platforms. Thank you.